Hi everyone. In this video I'm going to talk about testing a claim for a mean, a hypothesis test for a mean. It's really important that you watch the video on testing a claim for a proportion first, because it is through that one that I really go through what testing a claim is all about. In this one I just want to do an example. So if you find yourself confused about anything, please go back and watch that video. So the first thing I want to do is just like with testing, hypothesis testing for a proportion, really we just have the same set of steps for this time we're testing for a claim for a mean. So again, this process is really the same, except now our data is going to be quantitative, and thus we'll be able to have a mean and a standard deviation for either the population or the sample that we're looking at. So I want you to also look back at a confidence interval for a mean if you aren't sure about the t distribution in the t table. I have a video on that as well. So on this one, I'm really just going to do an example and go through how to do that how to do that test. So just like before, we have the 5 steps. We want to state the null hypothesis and the alternative hypothesis, and we want to be sure to identify which of those two is the claim. Because this is a mean, we will have a sample mean. So we need to identify the sample mean, and in whatever the problem is, we're going to have to find out if we are given a standard deviation for the population, or if we just know the standard deviation for the sample, in which case, and we determine the model here. So that means either we're going to use a normal distribution and the z and a z-score, or if we're given the sample standard deviation, we're going to have to use the t-model and find a t-score, which you should have a t-table for that. Okay, we have conditions to check, and those are just like with a confidence interval. If our population data is normally distributed, then we can just go forward. If not, we need to be sure we have at least a sample size of 30 or more. In step 3, which is where the bulk of our work is, here's where we determine we start out by determining the test type, and that's going to come from our alternative hypothesis. Do we have greater than, less than, or not equal to? So we're talking about whether or not we're going to have a right-tailed test, a two-tailed test, or a left-tailed test. And you're going to have a right-tailed test if your mean is greater than. You're going to have a two-tailed test if it's not equal to, and you're going to have a left-tailed test if your hypothesis is stating the mean is less than some value. Okay, so you decide which one of those. Once you've done that, you figure out your critical value, which is the z-score affiliated with your significance level, which is this alpha here, and you're given that in your question, some sort of critical value, critical space, level of significance. If it's not given, the default is always 5%. Okay, and then you're going to plot that on your curve, and then once you do that, you've got to compute your test statistic, which is also a z-score or a t-score, and you are going to find that based on the sample data that you have up here, and here are the formulas for finding that, and it's the formula for finding the z-score that we've used many times. It's the mean, the value of x minus the population mean divided by the standard deviation, and in this case, you should recognize this. This is the formula for the new standard deviation when we have a sample size, central limit theorem there. And so you're very familiar with this formula. And the t formula is really the same. We just use it as a t-table, and but we're still going to take the sample mean, subtract off the population mean, and divide by the standard deviation over the square root of the sample size. Okay, and once you've done that and you've come up with some sort of value, you can plot that, and then you need to find your p-value. And then what we're going to do is based on that information, we either reject the null or fail to reject the null, depending upon where that value is. Is it in the critical space? Is it in the alpha or not? And then finally, we interpret that conclusion. Is there or isn't there enough evidence to support the claim? In other words, if you reject the null, then there is, and if you fail to reject, then there isn't. So let's go ahead and try a problem. Okay, here is a problem that states that a light bulb manufacturer advertises that the average lifespan of their light bulbs is 900 hours. Okay, and let's say we're a consumer safety group, and here we are going to test this claim and make sure that they're able to put that on their boxes. So how are we going to test this claim? We are given a level of significance that they want us to use, and it is a 0.05 level of significance, and we are given the fact that the lifespan of a light bulb is normally distributed. Okay, so what do we need? We aren't given any sample data, so actually, in fact, they give us the data. They go out and they test 15 light bulbs. 15, they choose a random sample of 15 light bulbs. And what you're going to need to do with this is enter all of this data into your calculator. And if you have any questions how to do that, you can talk to me in class, but we've done this in class before. You're going to hit data, and you will come, it'll be brought to your list, and you just enter that data into your list, and then you will hit second stat, and it'll come up on one variable stats. You want to hit enter. You want to, whichever list you put it in, that's the one your data should be on. You just have single frequencies, so you come down to calculate. And once you hit that, you'll see that it'll bring you to a screen with all your information. You'll see that n equals 15. And we know that we see that the standard deviation, or I'm sorry, not the standard deviation, the sample mean of just this bit of data here is equal to 724 hours. So a little bit lower than the claim that they're making. And then lastly, you will notice on your calculator that the one underneath your mean says S sub x. That is your sample standard deviation. And when we're given a set of data, that's what we have to use. We don't know the population standard deviation. So our sample standard deviation we see is 157 hours. Okay? And sample deviations are always going to be a little bit bigger than population standard deviations because they're going to vary with each sample. So the overall average is going to be a little bit bigger. As the sample size gets bigger, then hopefully your standard deviation gets smaller until you slowly approach completely normal, closer into the mean. Okay, and or the standard deviation of the population. Okay, so step one tells us from the previous page, the first thing we need to do is identify our null and alternative hypotheses and to decide which one's the claim. So because the claim always has to be an equality, we are going to go ahead and say that the mean light bulb length is the 900 hours. Okay, and therefore our alternative hypotheses, now it's not saying that they're claiming that it's larger or shorter, they're saying that it is 900 hours. So in this problem, here is our claim. It's actually the null. We're going to do a test to see if we can reject that null, in that case the claim will not be true. So everything gets kind of switched a little bit, but we'll get to that in a few minutes. So, but our alternative hypothesis is not greater than or less than. It's just simply not equal to. Either it's equal to 100 or it's not equal to 100. So here's our alternative, but our claim is actually in the null this time. All right. Step two tells us to check the conditions, and I can see that we do not have 30, n is less than 30, but if you notice up here, we are told that is a normal distribution, assume a normal for the population. So I'm just going to write that down, that it's normally distributed. Okay, step 3 asks us to determine the test type. And if you forget any of this, just go back to our previous screen, rewind a little bit, and you can see what the steps are. But in this next problem, in this next step, we define the test. So here we have a two-tailed test. Okay, if you remember again from the previous videos, two tails is when this inequality here is not equal to. So what's going to happen is our alpha is going to get broken into both tails. So once we know we have a two-tailed test, we have to go ahead and draw the normal distribution curve, which I believe I've already done one. There it is. And we're going to start plotting a few things. The first thing I'm going to do is just go ahead and center the mean right here of 900. And we're not right-tailed or left-tailed, but we've got to go, we're going to be in both tails. So in fact, what's going to happen is our alpha up here is going to get broken up into two parts. So we're going to have half of it over here and half of it over here. So step A is just that. It's going to tell us to find the critical value and the critical space. Oh, and we were supposed to actually way back here in step 1, we had to determine which model we want to use. And because we are given a sample standard deviation instead of the population, we are going to have to use the T model. Cannot use the Z model. But as I remember again from one of the previous videos, the shape, it's still a normal distribution. It's just usually a little flatter. So we're going to use our imagination here, and this is going to be our T model. Okay, so our significance, our critical space is alpha equals 0.05. But because we got to divide this by 2, we're going to have to divide this by 2. If you do that on your calculator, you're going to get 0.025. So this side is going to have 2.5%. And this side is going to have 2.5%. I'm going to carry out one extra place. And if you go to your T table, I'm going to pull that up now. We'll just check that critical value for our alpha. All right, so remember when using the T table, we do have to remember to look at the degrees of freedom. So if I pull up the degrees of freedom for this one is always n minus 1. So for this problem, n minus 1 is n is 15. We have 15 pieces of data, so our degrees of freedom is equal to 14. So let's close this out, and we will open up our Z table, or T table, I'm sorry, T table, and let's go ahead and find that. So we are talking about in two tails. Now, notice that we have two tails here, so we're going to focus on that, and we've broken the tails into 0.025. So that's going to be roughly about, let's see, one tail is 0.05. Hang on. Here we go. Here we are in one tail is broken now 0.025. Notice up here above it says 0.05, and that's what we wanted. But for the two-tail test. So the two-tail test of 0.05 significance breaks down to a one-tail test of 2.5%. So whichever way, either way, it's the same column here. And then at 14 degrees of freedom coming across here, we can see that T equals 2.145. Okay? Okay, so our critical T value is equal to 2.145. All right, so that I'm going to go ahead and plot that here now. So let's just say it's about here. Here's our critical value, and it is a T value equals to 2.145. And again, because it's broken into two parts, the other critical value is over here on the negative side. So our second critical value is negative 2.145. All right, so alpha is this blue space here. It's just broken into two parts. So the sum of those two parts is our 0.05 significance. Okay, so that's our boundary. All right, so letter B says we need to go ahead and find that test statistic of our data of our sample data up here. And because it is a T model, we'll be using the T formula, although really it's the same. So our test statistic is going to equal the sample means of 724 minus the population mean of 900. I'm going to divide that by the standard deviation, which is our S, 157. Central limit theorem tells us to divide it by the population, the sample size of 15. And if you do all that on your calculator, you're going to see it's negative 4.342. Okay. All right, so what I'm going to do, I'm going to get a different color here so we can plot this in a little different color. So this is my test statistic. And I can just tell that here's where t equals -2. So -4, that's way out there. Remember, these are standard deviations. A t is just the equivalent of sort of a z-score. Works the same way. The only difference between a t-table and a z-table is more specific. We have less data when we have a sample standard deviation with less information. So our table's a little less detailed. But here is our test statistic here, and it's going to equal t is equal to -4.342. Okay, so just by looking, I can see that this p-value is going to be very, very tiny, and the other half of it is going to be an equal amount over here, the p-value. All right, it's just that it's on this side. Clearly, our sample data is way below the 900-hour lifespan. Okay, so the question is how much less? So just to quickly go through, how do you find the p-value? Let me go back here. So step 4 is the next step is we have to find that p-value. Well, p-value is equal to the area. It's equal to the area less than the -4.342. We don't have a z-table, so we really go back to that t-table. And you'll notice if you look at the t-table that you don't even find anything less than about 3. I don't have my table in front of me. But we're talking about basically a value of 0 here. Go ahead and change this. So this is going to equal roughly 0. It's just so far out. There's nothing below it. So our p-value is basically 0, and 0 times 2 is still 0 because our p-value still has to get multiplied. So the conclusion that we can draw is reject the null, right? Because we clearly, our p-value is less than our alpha. In other words, a p-value of 0 is much lower than the 5%. All right, so we can go ahead and reject that now. Now, normally, if you did get some value here, you would have to multiply it by 2. So with a two-tailed test, really, we have p-value is actually 2 times whatever you get. But in this case, 2 times 0 is still 0. So it really doesn't matter. But just keep that in mind if you do a problem where the p-value is greater than 0. All right, and then, so what do we do in the last step? We go ahead and draw that conclusion. Now it goes back to up here with the claim. We have to be careful in that, so what is our conclusion? There is or isn't enough evidence to support the claim that the average lifespan of light bulbs, I'm going to abbreviate here, of light bulbs is 900 hours. Okay, so the claim was that it is 900 hours, but we are rejecting the null. So if you think about that, it goes back to this whole thing where we would maybe draw a line right through the null. So actually what we're doing is drawing a line right through the claim. So really there is not enough evidence to support the claim. Normally it's switched, but that's because normally our claim is in the alternative. So just be very careful. That's why you can never sort of assume that you're going to do everything the same way. You really have to read your problems, really think about setting up your hypothesis, your null, and your alternative, and be sure to always identify where the claim is. Most of the time, the claim is in your alternative hypothesis, but this is one of those situations where the claim is actually the null. Okay, so this is an example of a two-tailed t-test with data given and so we have a sample uh, standard deviation. Go ahead and try some problems where you have a one-tailed test, either the left tail or the right tail. Remember, if you're given the population standard deviation instead of the sample, you use a t-test. So go ahead and practice some different types of claims. All right, testing claims.